We've been using integrals to find the area between two functions, but we can also use integrals to find the volume of a 3D figure. And the reason that this works is because we know that area has units squared and volume has units cubed. So to go backwards and add 1 to the power of the units, we would take the integral of area to get the volume. You'll notice that the learning target says apply integrals to find volume using cross-sections, so we need to start by defining what a cross-section is. If you look at this first figure, which is representing a of x, you are taking a three-dimensional figure and slicing it so that you create a two-dimensional shape with the slice, and that's called the cross-section. Then to turn that cross-section, which is two-dimensional, into a three-dimensional shape, we take the area of the cross-section and multiply it by the thickness, which we call dx, and that creates that third dimension and gives us a three-dimensional slice. So what we have here, I kind of like to think of this as like a bone, or it also looks like a really smushed loaf of bread. That is now one slice of bread with the thickness of dx, and that's the product that we see in the integral. So finally, what the integral does for us, it takes all of these slices of bread and adds them up, because we know integral means sum, and it gives us the total volume of this smushed loaf of bread. The last thing that I want to point out about the formula is that it is an integral with respect to dx, and that is because we are taking these cross sections perpendicular to the x-axis. So our limits will be a and b values, which are x values, and we'll see in a later example that it's possible to also take cross sections perpendicular to the y-axis, and we'll talk about how that changes the integral. Let's take a look at our first example, and I wanted to start with one for which we have both a two-dimensional and three-dimensional view of what's taking place here, because it's not an easy thing to start visualizing when you first learn this concept. So what you're going to see in the two-dimensional figure is the graph of the parabola bounded by the x and the y-axis. So we have this shaded in region that we're going to use as our two-dimensional space to create this three-dimensional object. The other thing we have labeled so far is this representative vertical slice. So what that means is this is one example of a cross-section that's perpendicular to the x-axis. Please know that I could have drawn that anywhere on the figure, and that there's actually an infinitely large number of vertical slices or cross-sections that we're making across this region. So now we need to make the leap from this two-dimensional figure onto the three-dimensional object that's created with these cross sections. So the best way I can describe what's happening here is I want you to visualize that this shaded region on our two-dimensional graph is like a piece of land. Maybe it's somebody's yard. And from that yard, we are going to have an infinite number of blades of grass growing straight out of that two-dimensional space or yard. But these blades of grass are really unique. They're not the typical blades of grass that you're used to. They're really thin and they're really wide, so they span the entire width of this region. And also the shape of the blades of grass are really unique in that they are perfect geometric figures. And so for each question, they're going to tell you exactly what geometric figure that is. For a lot of questions, it's a square. So I want you to imagine, and I know it's hard to visualize, there is a really wide piece of blade of grass that's a perfect square that's going to grow out of this representative vertical slice. And know that there are infinitely many of those blades of grass. And so when they all grow out of the ground and they kind of glue themselves together, it gives us this three-dimensional shape that you see here, and they're just again showing you one representative slice of that. Again, that's just one description. It's very hard to visualize, so I would suggest that you maybe do a Google search of some images or some videos of calculus volume by cross sections and see if you can get a better visualization of what's happening here. So even though you're still trying to digest what is actually happening as far as the visualization, let's go ahead and set up the integral and do the math part of what's happening. So we know that the volume is the integral of area, so we'll start with that thought. So we'll start by writing the integral of area. I do have dx because in the problem, and it will always tell you which axis you're perpendicular to, it is the x-axis. And I also know that the geometric shape of each cross-section is a square. So mentally, I'm thinking about the area of a square, and that is base squared. So my next thought is, well, I need to integrate b squared of these cross-section squares, dx. I look at the two-dimensional graph to get my x limits for my integral. So the region spans from 0 to 2 on the x-axis. Now the hardest decision is to come up with an expression for my base that I need to square. And knowing that each blade of grass is a square that sits on top of this yard, as we're calling it, since it goes all the way across, that will be the base of my square, and I have a square sticking up perpendicular from my paper. If you want to look at it on the 3D figure, the base goes there. And so the base at any cross-section is controlled by where this function is, or the y value of this function. And so the expression for that function we get from the problem would be 1 minus x squared over 4. So that represents the base of every cross-section. You'll find that a lot of these questions are calculated, not all of them, but just for the interest of time, I put that in my Math 9. The final answer would be 1.067. So that's the volume of that three-dimensional shape with all those cross-sections being squares. So let's look at actually the same two-dimensional graph, but this time we're going to find the volume when the cross-sections are perpendicular to the y-axis. So I mentioned earlier that doing horizontal cross-sections would change the setup of the integral slightly. So you'll see that now it's a dy integral because we're going to cross-section perpendicular to the y-axis. That also changes the fact that the y values now control our upper and lower limits of our integral. And we write the expression as a of y because the function will need to be written in terms of y. So we'll actually have to solve this function for x. But right now what I did was I just copied the two-dimensional graph. I won't attempt to draw the three-dimensional graph, but just know that these squares are now going to be cross-sectioned horizontally. So here's one representative horizontal slice. Just know I could have drawn that horizontal slice anywhere between 0 and 1 on the y-axis. So we'll start each volume cross-section problem with the same thought, that it begins with the integral of area, dy, because we're perpendicular to the y. The shape is still a square, so I've got b squared. My y values are from 0 to 1, so those are my limits. So the last thing I need to do is come up with an expression for my base. And I know this time it goes horizontally. But that length is still controlled by the function. It's just that I need to write that function in terms of y instead of x. So I actually have to solve the equation for x to get that expression. So I did my work off to the side here, and when I solved for x, I got the square root of 4 minus 4y. So you're welcome to pause the video and check out those algebraic steps. But I put that in for my base, and I will square it. And since we used our calculator on the last example, let's practice solving one of these without our calculator. The first thing that I noticed, and I hope you did too, is that we had a square root being squared. So I think to simplify it before we move forward, we would cancel that square and square root and just give us the integral of 4 minus 4y from 0 to 1. And now we need to come up with an antiderivative. Using the power rule, we get 4y minus 2y squared, and we'll use the fundamental theorem of calculus to evaluate it from 1 to 0. Plugging in my upper limit of 1 gave me 4 minus 2, and then when I plugged in the 0 to my antiderivative, I got 0. So final answer for our volume would be 2. A question I get often is, why when we use the same two-dimensional graph do we get two different answers for the three-dimensional volume, and we also still use the same shape, which is a square? And the best answer I have for that is that the size of the squares would be different if you slice them vertically versus horizontally. But again, I would just recommend that you search out some videos or images to see if you can get a better idea of what we're looking at for the three-dimensional figure. And we'll definitely do some more examples together in class.